your internet. But the title of the paper has changed a little bit. And it's still preliminary, so there is actually no paper, and we are still working on it, so I apologize for that. George will answer all questions, which is very good, and I'm very grateful for him to do that. So I want to start with a slide, and I wanted to explain the slide by saying that these are thoughts which we all have thought at some point, and I think the previous talk was confirmation that it's a widespread view that number one, equilibria in games come about through repeated play and some form of learning, that we learn how to play equilibria rather than sort of come up with the equilibrium without any learning process. So the second thought is that we very rarely play exactly the same game twice. So nothing is exactly the same. So even traffic is not, no day is the same as the previous day. So my view of this is sort of, I wake up in the morning, I see lots of signals in my environment, which could potentially tell me what traffic is going to be like today. And I have to somehow figure out what's relevant. And I have to figure out which differences between sort of various signal realizations are important and which ones are not. And that's sort of the question in which I'm interested in. So it's not just, so in our model, people will receive external signals. Every day they see these signals. And they have to learn how to play conditional on those signals. So there's some information about the game and changes. We have to figure out how to play conditional on those signals. And while we do that, we have to form some view of which signals are similar to others. Because if we refuse to learn from we only learn in exactly the same circumstances, it's going to take a long time. Exactly the word as it was this morning will perhaps not return in my lifetime. So it seems necessary that we learn from similar experiences in the past. And so the purpose of this paper is to form an equilibrium concept for games that is, we will call similarity equilibrium, and which is meant to capture that people get signals about the game and then they classify different signals as similar, and they choose their action conditional on having seen this signal and thinking of other signals as similar. Our purpose is to introduce this definition and then to relate it to classical equilibrium concepts of game theory. And the second purpose is to propose an explicit model of learning based on similarity. So this will be a dynamic model, and to try to relate the dynamic model to the equilibrium notion. So the questions that we are after is, on the one hand, if learning stabilizes, so we're not going to ask when does it stabilize, we're going to ask if it stabilizes, will an equilibrium be reached in the sense that we just came up with, namely a similarity-based, a similarity equilibrium. And the other question which we will ask is there some equilibrium selection? Are some equilibria more likely to be reached than others if there are multiple equilibria? I should tell you a few things about what to anticipate in the model, some things that will be specific here. In principle, a signal that you see could be relevant for two reasons. It could help you to understand what the game really is, but it could also help you to predict what other people do. So when you see information, there are both aspects to it. We are going to, in this particular paper, to make our task easier and cleaner, we're going to focus on the case that signals are payoff irrelevant. So all that they could do is they could help you to predict what other people do. And so, for example, you could attempt to use the signals in your environment to learn to play a correlated equilibrium. And the question, do you learn to play a correlated equilibrium, will be of interest to us. So we go to this extreme case in which signals are actually payoff irrelevant. The second point I want to make, also sort of to warn you right away, that similarity will be exogenous. We will not ask where does it come from. We will just ask, given this, if agents have this perception of what's similar to what, how are they going to end up playing? We are not going to ask in this paper, where do these similarity notions come from? When we think of similarity, two properties that will be important will be transitivity and symmetry. And so in the model that we propose, we will not assume that similarity is transitive. And so the argument is that, for example, 0 is similar to 0.01 and 0.01 is similar to 0.02. And I could go on up to 999.99 is similar to 1000, but 0 is not similar to 1000. So, so we will not assume it's transitive. We will also not assume that it's symmetric. So here the question is, if x is similar to y, is y also similar to x? And you might say at first sight, oh yes, that should be true. But let me interpret the notion of similarity a little bit differently. So if the reason similarity matters here is you see x and you think about what to do, signal realization x, and you think, oh, this is similar to y. So the way I want to interpret it is, if I see x, then y also comes to mind and my past experiences with that. And so if instead of saying something similar, I'm saying, oh, when I see one thing, the other thing comes to mind, that's not a symmetric relation. And here's my example for this. So whenever I walk in the street, I see a dog, and I see the dog, it reminds me of my dog. So in that sense, my dog is similar to all other dogs. But on the other hand, when I see my dog, it does not remind me of every other dog. I forget about the other dogs. So I have a contract with my dog who is in the background. The contract says she doesn't bark, and I mention her in the talk. And so far, she has stuck to the contract. And so, and moreover, I've slipped her in order to explain why we want to allow similarity to be non-symmetric. Okay. Now, here's a preview of what we find. So if we assume that our similarity notion is symmetric and transitive, so if we concentrate on that, focus on that case, then similarity equilibria will be identical to correlated equilibria. So there will be no payoff relevance, so then if it was payoff relevance, you would expect some Bayesian and Nash equilibrium here, but because it's not payoff relevant, it's really just a coordination device. So,
clarification, do all the players have the identical notion of similarity, or is it idiosyncratic?
It's idiosyncratic.
Okay.
They have idiosyncratic signals, they have private signals, and so the notion is of similarity is also idiosyncratic. Very good. The second is, well, we will propose a model of learning, and as I said, we want to prove theorems of the sort. If similarity-based learning does converge, it converges to a similarity equilibrium. And we will discuss this. This will turn out slightly complicated. So at one point, I will only be able to present a conjecture, not a result. One result and one conjecture on this topic. And then finally, we wanted to study whether similarity learning selects among equilibria. And we will give examples in which, in principle, the signal structure would allow agents to implement a correlated equilibrium. But the fact that they sort of link signals to each other by regarding them as similar prevents them from doing that. And with probability 1, they end up ignoring the signals they receive and just play a pure strategy in Nash equilibrium. So we will prove that for a class of games. Here's a slide of related papers, just in case that these papers, these references drift through your mind as I'm speaking. So the one related paper that you might think of as Gilboa and Schmeitler on case-based decision theory, in which they've axiomatized a decision maker who chooses expected utility maximizing based on a numerical similarity relation. So in that paper, similarity is expressed by a numerical function, which therefore reflects whether one thing is more or less related to another. So that's our notion is binary. Our notion will just say, oh, it's either similar or not. We will not use a more or less similar notion. And of course, we can see the attraction of doing that. That's no doubt that that's an attractive thought. But so for simplicity, we're not going to do it. We are going to be interested in games. We are going to simplify a little bit. But some of these ideas, for example, of transitivity and symmetry also show up when you look at numerically valued similarity functions.
Tilman, we have a question from Eva. Eva, would you like to unmute yourself?
Yeah. So, you know, if players in a repeated game use this no-regret learning that I like, then they're going to converge to correlated equilibrium anyhow. Do these signals somehow help them? Like, do you have a result saying that the convergence is now faster, or?
So the theorem that you're quoting is Hart-Masquelet.
Exactly.
So Hart-Masquelet does not say they converge to the correlated equilibrium. Hart-Masquelet says they converge to the set of correlated equilibria.
Sorry for the imprecise words.
Those are very different things. But my own experience, so let me postpone that. So my own experiences, I've spent many in the class of games that I'm going to present at the end. I've spent a number of a significant proportion of my time simulating the Hart-Masquelet algorithm, and it actually always converges straight to a pure strategy Nash equilibrium. So in Aumann's famous example, the Battle of the Sexes, Hart-Masquelet's algorithm misses the correlated equilibrium all the time. So numerically. So it does converge to the state of correlated equilibrium. Even better, it converges straight to a Nash equilibrium.
Well, that's true in some cases.
Yes.
Like.
Yes.
Okay.
So I have. So I think there are. Let me bracket that out. So, and there are many other things to say. So our players will play variable games all the time. So we have to ask. So Masquelet's players play a fixed game all the time, and so on. A paper that has actually used the Gilbert-Schweitzer idea in the context of game theory is Steiner and Stewart in Theoretical Economics 2008. And there is a lot of connections between that paper and ours. So that paper looks at a particular class of games and aims for a particular result. All of these are different from what we do, but that is a closely related paper that I just want to acknowledge. There's also by Isaac Gilboa and his co-author Rosella Agenciano work that applies Gilboa-Schmeitner style ideas to learning in games, and it's different from us. What also might come to your mind is the work that Philip Giel has done on analogy-based expectation equilibrium. And there, all that I want to say is in Philip's work, analogy is a partitional relation, which means sort of the similarity relation is symmetric and transitive in this case. And so we are interested in cases in which that's not true. I showed you an overview of where we are going. I'm going to show you also what we plan to do in future work. So really, we started this interested in learning in incomplete information games rather than learning in complete information games. Learning in incomplete information games rather than learning in complete information games. And we were interested in the question whether agents can learn to behave as if they had infinite hierarchies of beliefs, and as if their behavior depended in some complicated way on higher order beliefs. So we have games in which equilibria depend in sort of discontinuous ways on higher order beliefs, and we were wondering, but can you realistically learn to play such an equilibrium? And the difficulty in which we are interested is, in particular, sort of, so if you want to learn repeatedly in an incomplete information game, do you really have to rely on observing exactly the same type twice, or can you learn from similarity? And so we still plan to pursue that. This was my introduction. If there are further questions, let me check my time. Very good. So I'm starting off by explaining the equilibrium notion, and then I'm going to introduce the dynamic process. So, and I'm going to introduce the equilibrium notion just for the case of, so we're just going to talk about the case of two players. We look at a game in which the action set is finite. So for each player, there is a finite set of actions and a von Neumann-Morgenstern utility function. Before the game is played, each player sees a signal. The signal comes from a finite set of possible signal realizations. So theta I is what player I observes before the game is played. And theta I is distributed according to a distribution function f, which we allow to be very general, except that it has positive marginals, so that there is no signal that is never observed. That would be absurd to include in the model, but we want to allow correlated signals or perfectly correlated signals and so on. The similarity notion is described like this. So it's described by a correspondence which takes every signal and tells us what's the set of signals of which you think that they are similar to the given one. So if you see theta I, which other signals will inform what you choose when you see theta I? So that's a set which we call Si of theta I. The similarity notion, so it's individual, it's for player I. Of player I, it's a set that depends on theta I. It maps capital theta I, the set of all possible signal realizations, into the power set of all possible signal realizations except the empty set. We will assume that it's reflexive, so that what you see is similar to itself. So in other words, you see theta I in some periods. So you, one of the experiences that will inform your play is whenever you saw theta I before. But it could or could not have these two other properties, symmetry or transitivity. So symmetry means if theta I hat is similar to theta I, is theta I also similar to theta I hat? And we don't, in general, assume this. But sometimes we look at the implications of this. And the other property is transitivity. If theta I hat is similar to theta I, and theta I tilde is similar to theta I hat, is theta I tilde similar to theta I? And again, we will not assume that necessarily, but we will sometimes look at its implications. If these two properties are also satisfied, then similarity is partitional. That is, I can partition the set of signals that player I sees into subsets and say everything in this subset is similar to each other and everything in that subset is similar to each other. But if I violate these, it's no longer partition. And here's the equilibrium notion. So first I have to define what's a strategy of player I. A strategy of player I says, if you see signal theta I, what are you going to do? So here's the definition. It's just what you would expect. So strategies sigma 1, sigma 2 form a similarity equilibrium if for every player, for every type that this player might be, the player chooses an expected utility maximizing action, where expected utility is maximized not just conditional on theta I itself, but also conditional on signals that were similar to theta I. So I'm going to sort of ask, what is the conditional distribution of other players' actions? Not just conditional on theta I, but conditional on the set of all signals that are similar to theta I. If you look on the right-hand side, this is sort of a conditional probability. You see that I just multiply by f of theta I hat, theta j. So in other words, so I multiply by the probabilities without normalizing them. So to make this a conditional probability, I would have to divide by the total probability that you see a signal in the set Si of theta I. But for the maximization, that's irrelevant. So I've dropped that on the right-hand side because it's just a constant. So it just says, so given your signal, think back of all the cases in which you have seen this signal or a similar signal, and then calculate the corresponding conditional distribution of the other player's actions and optimize against that, player and expected utility maximizing strategy against that. If all players do that, simultaneously we have a similarity equilibrium. Okay, so in principle now we could go on and study the concept of similarity equilibrium and apply it to various examples and do this or that. So we are not going to do a lot of that, in particular not in the time. I want to state two things. I want to relate it to correlated equilibrium. There is a question. Shall I? Rahul is raising his hand. You're supposed to click on raise your hand.
Sorry, Tilman. Can I just ask a question about the interpretation of the concept, the similarity equilibrium, in particular because your dog example was so salient. So what does this mean? So if it's basically saying that I am somehow treating the signal of seeing my dog as I can't really tell that apart from seeing other dogs. Yes. Is that what?
Yes. Well, no. So my dog might be listening, so I have to modify this a little bit. What I wanted to say is, my dog. When I see my dog, it doesn't remind me of any other dog. It's so unique. So I just think of all the other occasions my dog and I have had together. But when I see another dog and think about how should I interact with that dog, I am, among other things, I remember my own dog. Yes.
I mean, I guess I'm just asking for an interpretation of these signals here. So like, what should I think of these signals as being? Is it just something that I can't tell apart?
I see. So you can tell them apart to some extent. So in general, you would think of it as you wake up in the morning. My version of that is actually also traffic. It's also my favorite game. And my impression is with the traffic game, you wake up, you see lots of pieces of information in your environment. You have to think about, are they relevant for which mode of transport I'm going to choose and which route I choose this morning? And so, for example, there is the weather, but I'm not going to look at exactly the temperature today. I'm going to think, oh, it's warm.
I see.
Right. And then it's a case here in which, so it's a little bit stylized in the sense that the signals actually are irrelevant for the payoffs. They gain their relevance endogenously. Because if other players watch them, I should watch them, like in correlated.
Thank you.
Tilman, can I ask you a question?
Yes.
It seems you treat all similar signals equally, I mean, as to the signal you have at hand. So you see another dog, then you think of your own dog and other dogs and so on, but you treat them in the same way. So you don't give any prominence to the one that you see in front of you.
Right. So I think this is, so sorry I interrupted you, but I'm guessing your question is, oh, that's not plausible.
No. I just wanted to clarify that you don't give any particular weight to the signal you have. You think of all the ones that you think of as similar and you treat them in the same way, right?
Yes. So So then maybe this was just, I felt, oh, you should say that's not plausible because of course it's not so plausible. So Geboa-Schmeidler I have a weight function, right? So I see my dog and I see a dog and sort of, at first I think, have I met that dog before? And that should have high weight. And then I think of some other dogs I've also met before and they look similar, same race or something, that should have some weight. And then I see this dog over there and she never moves actually, so it's just a stuffed animal as far as I can tell. So that's low value. And we are not doing that. But so this would be, if we wanted to directly apply Geboa-Schmeidler's case-based decision theory, then we should do that. But we have not done that. But not because we wouldn't find that interesting, just for simplicity. All right, so let me move on a little bit. So one thing that one can do is one can take a similarity equilibrium and then ask yourself, so given that these signals are not payoff relevant, let's boil it down to what it really implies about the distribution of actions in the game. So I can derive from it the distribution over actions. There's an implied distribution over actions, and so here's this claim that there is a relation between correlated equilibrium and similarity equilibrium, but only when sufficient condition, if both players are, correspondences are symmetric and transitive. So if similarity is a partitional relation, then a similarity equilibrium will be a correlated equilibrium, because you can think of the partition element essentially as the state of player I, or as the signal that we're going to send to player I. If they are not, then you can easily create examples where similarity equilibria create action distributions that are not correlated equilibria. So here is an example of a game. On the left-hand side, the game is a two-player game. Player one has 2 strategies. Player 2 has 3 strategies. On the right-hand side, I write down the signal distribution, and the signals are perfectly correlated. Each player can see 1 of 3 signals, but they're actually perfectly correlated. And each player thinks of the first 2 signals as similar to each other. And so the similarity correspondence says, if I see theta 1 hat, oh, I'm also going to think about what happened when I saw theta 1 hat. If I see theta 1, I also think of theta 1 hat, and vice versa. And then the third point says, oh, if I see theta 1 tilde, I'm also going to think back at theta 1 hat. That looks similar to me. And so that's sort of, we're going to ask sort of what happens conditional on this. So it's not symmetric, it's not transitive. And so they're claiming that there is an equilibrium in which conditional on the first 2 signals, each player plays A, and conditional on the third signal, each player plays B. And so how come? When you see the first signal, if these are the equilibrium strategies, you see theta 1, you think, oh, let me also remember what happened for theta 1 hat. But in both cases, the other player played A. And so if the other player plays A, your best response is A. That's true for both players. Therefore, these choices of A are best responses. If you see this third signal, you also remember theta 1 hat again. And therefore, you think, oh, with probability 1/2, he plays A, and with probability 1/2, he might play B. And so you have to ask yourself, what's the best response to that? And for player 1, it's clear, it's 1/2 times 1 plus 1/2 times 0 versus 1/2 times 0 plus 1/2 times 2. So that's B. The B is the better choice. And for player 2, it's the same. A and C against the uniform distribution over A and B have expected value -0.5, but B has value 0. So that's a similarity equilibrium, and the implied action distribution is this: with probability 2/3 both players play A, with probability 1/3 both players play B. Somehow it has evolved that's how they condition on signals. But this is not a correlated equilibrium because if we had this action distribution, I told player 2 to play B, player 2 would think, oh, if this is the action distribution, player 1 is going to play B as well, and my best response to B is C. So I have written this such that the best response to B would actually be C. But because player 2 mixes this up with what player 2 does on a similar signal, but not the same signal, and therefore thinks A is also a possible choice, he chooses this middle strategy, which is more like an insurance strategy rather than a best response to one of the other two strategies. So he overweights, in a sense, what player 1 does, conditional on the second signal. And that leads to an implied action distribution that's not a correlated equilibrium.
I have a question, Tilman. I don't know how to. Mm-hmm. So in the absence of symmetry and etc., is every distribution a similarity equilibrium distribution for some F?
Let me rephrase that question. Is every distribution of a rationalizable strategy or of a iterated deletion of dominated strategies? And I don't know. All that I have thought about this is that I thought, oh, I have to ask the question, is it, I have to first eliminate the dominated strategies.
Tilman?
Mm-hmm.
You may ask the same question by, here you are assuming a common prior, of course, right?
There is a common prior here, yes.
So if you don't have a common prior, there is more chance that you get everything if you allow.
Yes, but of course here the common prior is also, it's disturbed by the similarity relation. Right? So it's transformed by the similarity relation.
Yeah, okay.
So this paper is really closely related to Steiner and Stewart. I don't know whether they are here. Too many people here, but we should. So they construct, they prove a theorem of the form that in their setting with a numerical similarity measure, every equilibrium, so to speak, given the similarity measure, is the same as, even though there is an objective state distribution underlying, that the similarity measure translates it into subjective priors, because the similarity measure is subjective.
So your dynamic or your convergence theorem that we haven't seen yet depends on the common prior, or it?
So it depends on. So let me move to the dynamic model. Let me take that position. That theorem is.
Okay, let's see.
It was said something sort of happens with probability 1, so I have to have some probability measure with respect to which.
Okay, I see. Okay, good.
I don't know what I would say if I didn't have an objective. So many people, I've never given a talk that so many people could be lurking in the background and come up with some excellent question. George has to help me. Very good. So now it comes. Now we are going to write a learning model to try and find some underpinnings for our equilibrium notion. So time is discrete. In each period, each player first observes a signal, and signals are IID across time. But within each period, distributed according to this objective distribution F. So among themselves, within a period, of course, they can be correlated. We're going to index the actions now by T. In every period, the player takes an action. So the history of the system is a sequence, a finite sequence of pairs of signals and pairs of actions. Each player observes in every period their own signal, takes an action, and then observes both players' actions. And we will assume that we start with an initial history that's exogenous and that is rich enough so that players, when they try to apply the learning algorithm, look back and they find some relevant experiences, regardless of which signal they get. The learning algorithm is very naive in each period. after the initial history, each player observes their own signal. They look back at the last capital N instances in which they saw a signal that's similar to the one that they have just seen. And then they best respond to the frequency distribution of the other players' actions in those periods. And notice this capital N, that's the number of instances you're willing to contemplate. And so it matters a little bit whether N is finite or infinite. So I'm going to call that finite memory when N is finite. Sometimes these instances might be very far away. So finite memory only in the sense that you keep a finite number of instances in your memory. It may have happened a long time ago, some traumatic childhood event, but it stays in your memory. But it's a finite number of things that stays in your memory. And it's infinite. You just go through your whole life history and think, when was I ever in a situation like the one that just happened? And now we're going to introduce the random variable on which we are going to focus. In each period, we're not so much interested in what you actually observe and what you do. We are interested in sort of your strategy in that period. I can ask for every period, what would you do if you saw signal theta I and applied this learning algorithm? And I'm going to call that AIT of theta I, and the answer to that also depends on the size of your memory, so it's also going to be indexed by N, and it's a random variable, and has a distribution that's ultimately driven by the function f. Okay, so that's the model, and now I'm going to show you two results. Both of the results are attempts to say, well, if learning succeeds in the long run, if it stabilizes in the long run, it has to stabilize around a similarity equilibrium. And we think that's easier to say when memory is infinite. Then we have sort of a version of fictitious play. So if you look back, you collect only some of the past is relevant. So some of the past is irrelevant given the current period. Some of it is relevant. You look at the frequency distribution of the other players' actions in those periods, and you best respond to that. Now, what we want to say is if you converge, then you have to converge to a similarity equilibrium. And we want to state a theorem that makes it easy for us. So we're going to say if you almost surely converge. So if it's almost certain that you hit a time period after which you always take the same action when you see signal theta I. So if it converges to in the sense that whenever you see signal theta I, you do one thing, whenever you do something, see another signal, you do another thing. So if your behavior, for each player, behavior converges to a fixed strategy in finite time with probability 1, to the same fixed strategy with probability 1, then this pair of strategies has to be a similarity equilibrium. So I think the strategy here was to write that down so that it's trivial, so, so that there isn't much to say to prove it. I think that's the version that makes it trivial. It is much harder for the case of finite memory, because we can't really require that you play the same strategy given a signal with probability 1, because you only remember a finite number of instances. And that might be a very biased sample. So you might have seen a misleading sample. With a finite sample, there's always a probability that it's just wrong. With an infinite sample, the good thing is they tend to get it right. But a finite sample will always sometimes get it wrong. And so the statement cannot say you have to play with probability 1 a given strategy. It's going to say you play with probability 1 minus epsilon, a given strategy. So what we want to do is that we want to have a result that says there is an epsilon such that if you play a given strategy with probability at least 1 minus epsilon, then that strategy will be a similarity equilibrium. Now, as you can see, this slide says conjecture, because we haven't written down a complete proof. We think we know roughly how to prove this. We haven't done it completely. And you see that there is some red text there. That red text is there to warn you. For example, there is the phrase, assume there are no indifferences. And you might want to ask, what does that really mean? And the shortness of time will not give me an opportunity to say what that means, but there is a lot hidden behind that. And then you will notice the order of quantifiers. There are explicits and epsilon, such that for every n, for every memory size, the following is true. If you play the same strategy, ultimately with probability 1 minus epsilon, then the pair of strategies has to be a similarity. So take that.
Tilman, on that, we have just 2 minutes left.
Yes. So actually, I thought George is going to use those to prove this theorem, but I have a sense he is not standing ready to that. So there is a third part. So these were all 2 theorems. I'm going to wrap up. So the third part asks, let's study a particular class of games, and let's study similarity-based learning with finite memory. It's going to be with finite memory in this class of games. It's going to be our 2x2 games. We're really general here. Moreover, we are requiring that AA and BB are strict Nash equilibria of this game. And here I have just written as an example one such game. The example is chosen carefully because it's the game of chicken a little bit transformed, but it has a famous correlated equilibrium to be found in Aumann's papers on correlated equilibrium. And the objective is sort of to put some assumptions together and then to say, under those assumptions, you converge to a pure strategy equilibrium with probability 1. So this game has famously an attractive correlated equilibrium that gives sort of the players a higher expected utility, both players then randomizing over the 2 pure strategy equilibria. And we wanted to do put conditions together so that you will not learn to play that equilibrium, even though the signals in your environment would make it possible to play that equilibrium if you perceive them completely carefully. But if you mess things up, you won't. And the argument is not too subtle, not too unexpected. The argument uses the fact that sort of we need to construct a similarity relation where everything is connected to everything else. So that randomly misleading samples can propagate. And this is what assumption 2 here does. It says something of the form, everything is related to everything else. Assumption 1 is an assumption that says, it says the opposite. Actually, no, not everything is related to everything else. So it facilitates asynchronous learning with positive probability. We also needed that in order to state this result. But so the third set of results is that in games like this, we can find conditions that look maybe not too implausible, where similarity-based learning will not allow players to recognize, even if we give them in their environment the signals that would support a correlated equilibrium. They're not going to figure it out. This is the end. 3 things. So definition of equilibrium, the learning process, and if it stabilizes, does it find the equilibrium? And third point, and does it select? So does it actually find nice correlated equilibrium, or maybe just boring Nash equilibrium?
All right, excellent. Thank you so much, Tilman, for a great talk. I think we're out of time for questions.